Hi, hello everyone. So this is our first lesson. First of all, I will give you some a little bit orientation about what you should have right now. Okay, so please first you should check if you have OneNote. If you can go to our OneNote in our first content page, there should be teaching sequence. Okay, so and in that teaching sequence, I've upload the first term, the sequence for the first term. Okay, you see on week 9, there will be exam block for data test. That's the only assessment we will have for the first term. And we will work on that data test. You will know what data test is later. Okay, but since we've lost our first week, so that means we need to make that up at some stage, right? Possibly we can't cover all our unit 2 right here, but that's okay. So you don't need to worry that too much. We will come up a way to solve it. All right, and if you click thermal physics, so there are 3 handouts right here. These are the handouts you need to download. Okay. Okay, let me write the handout right here. Okay, and there's some video link for your study. All right, I will put more video links there. I will put my video links into the OneNote as well. But at the moment, that's what you've got. Okay, so our first lesson is about kinetic theory model. I'm not sure how many of you have heard that before. Okay, kinetic particle model is about the model about how particles behave in solid, liquid, and gas. All right, and that's the name for the models we call kinetic particle model. Okay, so I would like to take only half lesson for that. So for the video, possibly it will take me 20 minutes. I try to finish that within 20 minutes. Okay, but it's a little bit different from having a face-to-face lesson than videos. Okay, I will try to get you engaged, but all right. So this is different to face-to-face lesson. So you need to engage yourself more. Okay, because I can't ask you any questions. So when I ask a question, you try to answer it. Okay, I can't hear your answer. All right. Okay, so for each handout, there will be a syllabus. That's how things were set in the syllabus. Okay, so for example, kinetic particle model and heat flow. Okay, so first we need to describe the kinetic particle model of matter. Okay, and you need to distinguish a few terms. So some of the terms we will see in this lesson. All right. Okay, and this is the whole course structure. Okay, so in physics, we will have 4 units. Okay, so okay, we will try to cover unit 1. Okay, in our we'll try to cover topic 1 and topic 2 in term 1. Okay, and then in term 2 is more about topic 3 of unit 1 and topic 1 of unit 2. And the third, it will be the rest of topic 1 in the unit 2 and topic 2. And okay, so unit 3 and unit 4, they are for the external examination. You should have known that. And unit 1, unit 2 is more for the internal assessment. Okay, so here's the thing. So here's the handout. So I leave some space for you to fill in. All right, so that's why you need to get this physical handouts in front of you, not an electronic one, and also need to have a pen. Try to copy down the things. All right, and okay, let's begin. Kinetic theory model, kinetic particle model. Okay, the word kinetics, what it means? It just means related to anything related to motion. Okay, so kinetic particle model means how particles moves in matter. All right. Okay, so in a kinetic theory, it proposes what? It proposes that all matter is made of. So you should know that, made of small particles. Okay. Sometimes you can say molecules, and sometimes you can say atoms. Okay, but normally we prefer just particles. In chemistry, molecules and atoms, they are different. In physics, we use them interchangeably. Okay, and in kinetic theory, we propose that all matter is made up of small particles. Okay, and those particles, they are not static, but they are in motion. But what kind of motion they are in? All right, so let me show you some simulation, and you could answer that by yourself. Okay, let's go to, okay, so this is the online source from, okay, so interactive, oh, sorry, yeah, here it is. All right, so you see, when I say solid, okay, let's play solid a little bit. So that's what happened within solid. So you see all particles, they line up all the particles, but they are in motion. It's kind of motion of small amplitudes, and but so we can say they are sort of in vibration, and they keep moving. So that's a constant motion, and you can't tell which direction each particles are moving. So that's why they're random. Okay, but you see in solid, they're more or less in a very fixed positions. Okay, so what happens in liquid? Okay, you see in liquids, the particles, they have more freedom to move around. Okay, but still the separation between particles are quite small, even though they're bigger than what happens in solid, but they are still very close. All right, and what happens in gas? So that's gas. You see particles, they are moving much faster, and also there's no definite separations between them. So that separation are much greater than that in solid and liquid. And also in terms of motion, you can't tell which particle will move in certain direction. They are moving randomly in all directions, and also they keep moving. That means there are constant motions among themselves. Okay, so that's how can we visualize, understand the kinetic theory. The part of kinetic theory is about, okay, how can we describe those motions when they are in different states of matter. Okay, all right, so that's why the keywords here should be, first, they are in constant. That means they are always moving. And random. That means you don't know which direction a particular particle will move in at the particular moment. Okay? Okay, and also we see that three states. So that state means whether it's solid, liquid, or gas. Another word for this is phases. Okay, we can say different states of matter or different phases of matter. Okay, so this one is gas, and this one is liquid, and this one is solid. Okay, so how can we describe them? So description. Okay, so describing states of matter in solid. Okay, so you see the particle, they are bound together, right? They can't they can't go too far from each other. Okay, so they are tight, they are compact. All right. So how can we keep this kind of separation and keep the a definite shape for the whole solid. Okay, so we understand there are forces between particles. Otherwise, they will just fall. They will just go apart. All right, so that means they must be attractive. But once they are too close, then they bounce back. So that means they will have repulsive as well. So there are attractive and repulsive forces among themselves. Holding them in a what kind of arrangement of lattice? Think about this word. Okay, it's kind of very stable. Okay, so that's why when we look at a solid, like a piece of paper which is solid, the shape is quite fixed unless you fold it. Okay, or you saw a stone which is a solid. Okay, so without any external forces, the shape will be quite stable, right? And we describe this kind of constant motion as vibration, right? They vibrate. And also their vibration doesn't have a very large amplitude. They can only vibrate a little bit from their equilibrium positions. Okay, so that's what we call equilibrium. Okay, so how about in liquid? All right, so in liquid, particles have freedom to move. In solid particles, they don't have freedom to move. They only have a little bit freedom to vibrate, but they can't move around. Okay, so in liquid, particles have freedom to move within themselves and take the shape of. So when you fill in the water into a cup, and the water will take the shape of the cup. Okay, when you fill in another like a bottle, you will take the shape of the bottle. So the cup and the bottle, they are containers. And how about the volume? The volume won't change, right? So we know that the liquid can be deformed according to the shape of the containers, but its volume is always constant. How about solid? Solid can't take the shape of the volume. Can't take the shape of containers, and its volume is also constant. All right. The last one is gas. In gas, particles have freedom again. So the particle obviously can move away from each other. It's not just move within themselves. They can move away from each other for good. All right. The attractive force between particles is the weakest. There is some degree of attractive force still between the gas molecules, but those attractive force is very, very weak. So it's not significant anymore. All right, to keep them together. So that's why the gas molecules are free to go from each other. All right, gas will take both the shape and the volume. Okay, so that means gases, they don't have definite volume. So if you put the gases in a container, you will take the volume of the container. If that's a sealed container, so I think I need to emphasize that a little bit. It should be a sealed container, right? Okay, so how it works. So let me draw you a little some kind of picture to explain. Okay, so let's say if you have a sealed container. Okay, so this is a cup. Okay, so this is a sealed. Okay, so it has a lid. Okay. Okay, so if I put 5 gas molecules, okay, and you will take all the position. Let me draw it properly. Okay, you will take all the corners of the cup. So that's why you occupy the whole cup. Okay, you will distribute that 5 molecules, and as uniform as possible towards every part of the cup. So that's why it takes the whole volume and also the shape of the cup. All right. But if you put that into another cup, like if I have a cup in this shape, oh sorry. Okay, so it's a smaller cup and with different shape. I have a lid. Okay, in that case, if I still get that 5 gas molecules in it, okay, you will squeeze in a smaller cup and you will take the shape of the cup as well. So that's what we call the gas molecule. They can take both the shape and the volume of the sealed containers. That's it. Okay. So, and also this is another illustration. You see the solid, the shape itself is definite. So no matter what kind of container you put in, you will keep its shape, but not the liquid. The liquid will spread out and will take the bottom of the cup. All right. Okay. So, and you can have a good guess of this. What will be the ascending order of forces between the particles, and what's the ascending order of the speed of the particles, what's the ascending order of density of matter, right? So let's do it really quickly. Okay, so ascending order forces, we have said that before actually. So ascending means you need to do it from smallest to the greatest, right? So the smallest force should be in gas, okay? And then in liquid, and then in solid. So that's ascending order forces. So how about the ascending order of speed? So that means how fast they're moving, and also the density of matter. Okay, I'll give you 2 minutes to try to have a thought, to think about that. Take your time to think about that and to fill in your answer right here. Okay, I will pause the video so you can work for that 2 minutes. Okay, I hope you've got your answer. You've done your thinking, right? Okay, so let's say speed, of course, in solid, the molecules are only allowed to vibrate a little bit around its equilibrium positions. So that's why the speed should be the lowest. And the liquid, okay, and the gas. So you can see the previous simulation. You can see the molecule in the gas, they just flying around crazy, right? And ascending order of density. What do we mean by density? Density just means mass per unit volume. Okay, so mathematically, density we use the formula, use the mass of the object divided by its volume you occupied. Okay, so obviously, if you have a look from the above figure, you will see, oh, obviously, the gas, okay, if the mass are the same, you occupy most of the volume. So the gas normally have the lowest density, and then always liquids in the middle, and the solid. Okay, so these are very basic understanding of the description of our different states of matters. Okay, there are some examples. Okay, so that's example 1. So first of all, just ignore those 16 because I took those questions from some examination board. So that's why you see some question number which doesn't match the number of word examples. All right. The first one, the diagram shows how the atoms in a substance rearrange themselves during a change of state. Change of state, that means you from one state to another. Okay. So obviously you see, oh, those molecules, they are not packed together. Okay, so this must be gas. Okay, here you see the molecules, they are packed, but they are not in a lattice arrangement like a solid. So it's not a solid, it's a liquid. Okay, so that's gas to liquid. So it's very easy, isn't it? Okay, so and the molecule or substance become more closely packed and move more quickly. More packed and move more quickly. Okay, what happened? What's happening to the substance? What's happening? So gas being heated and compressed. Oh, okay. So being heated, we understand you give it more energy, the molecule move faster. But how about compress? Compress means that means your volume tends to be lower. So you have lower volume. So that means it can't be closely packed. Another word to describe closely packed means denser. Oh, sorry. I think I make a mistake here. Okay, so volume is smaller. So yeah, so that's denser. So volume becoming smaller does it mean it will become denser? Yes, because we know the density is just mass over volume. So if you have smaller volume, and the mass is the same, then density will be greater. All right, I hope that makes sense. Okay, so this looks like the answer for A, but how about B? Being heated and expanding. Oh, sorry, that's not the one we need. Okay, so B is not the answer. Liquid is boiling. Okay, this one is really interesting. Okay, and because boiling, it becoming gas. So it becoming gas. So from liquid to gas, it expands. So that means it can't be closely packed. All right, more closely packed. Okay, liquid is evaporating. Again, liquid to gas. All right, so evaporating means liquid becoming gas. So that means it can't be more closely packed. Okay, so the only answer is A. Good. Okay. Um, I would like you to take your time, try to work on example 3, and also example 4 is they are very easy. They are really very easy stuff. And also example 5. Okay, all these three questions, you will only take you, example 3 to 5, I think at most 5 minutes. Okay, so just pause the video and read the questions carefully and spend 5 minutes. Okay, right. Okay, so we're back. Have you made up your mind? Okay, so sealed plastic bag. So it's a plastic. So plastic, that means the shape of the bag can be changed, right? So plastic means flexible shape of the bag. Placing in refrigerator to cool down. So that means the temperature will drop. Okay, how do the gas molecule behave when this happens? Okay, so first of all, when you cool down, when the gas is cooled down, it should move slowly. Okay, and also when you move slowly, you can imagine when the shape will contract a little bit, and because that's plastic bag, the shape of the plastic bag can also become contract a little bit. So that means they are closer together. So it's very intuitive answer, right? Okay, water spilled on the ground. Okay, so it's water spilled on the ground. A hot day evaporates. So evaporate it's always liquid becoming gas. Okay, so change your arrangement. Okay, change your arrangement. It must be liquid becoming gas. Okay, so C and D starting with liquid, and that's gas. and this is solid. Okay, so the answer is C. Okay, which line in the table describes the property of solid and of liquid at a fixed temperature? So the temperature is the same, but what the property of solid and the liquid? Okay, solid, definite volume and definite shape. Good. Liquid, no definite volume, but definite shape. No. It should have definite volume, but no definite shape. Okay, so let's see, this is correct. Definite volume, but no definite shape. Okay, so answer is C. Okay, that's it for our first half of the lesson. Okay, so if that was a face-to-face lesson, then that would have been half lesson. We still have a half to go on the heat and internal energy, but I will put that in next video. Okay, so you might just take a break and come back and finish this for today, right? Okay, see you later.